Thank you. Welcome. It's always nice to be here again. And I will speak, like you said, about the joint project with Baby. And I start with an example. It's not, we are both more working theoretically, so we're not so much interested in the example, but it's always nice to have an example to understand what it's about. And our example is about light pollution. So we emit a lot of light during night, and that's a problem for nature, maybe. And since I'm now in the Netherlands, I look at night pollution of the Netherlands, like you probably can see here, because you can maybe see here is Amsterdam, and here's Leiden, here's Utrecht, and you can also see probably where Dortmund is here. You've probably found it already around here. And so light pollution is a problem, so we want to see, what causes light pollution, and well, we all agree that humans cause light pollution, so probably has to do with how many people are living in a special area, so we can look at this data too. This is measured, by the way, by a satellite going around the Earth, and basically records how much light is emitted through in the direction of the satellite. And you have data from the Netherlands, and you have, for example, the population density in all these districts here, more than 3,000 districts in the Netherlands. And more yellow means higher population density, more blue means less people living there. So usually Netherlands very highly densely populated. And you see here's a lot of yellow and here's a lot of red, so probably there's some dependence, and we can construct a data set based on this. So we have, for every of these 3,000 districts, we have the population density, and we have the average light emissions in this district. You can compute this. And then you have more than 3,000 data points. So I took the log of the population density and the log of the light emission. And then you get this nice scatter plot here. And it looks very much dependent. We always already see this. And if you have no clue of statistics, then you would want to have a measure for dependence, and then you read the book, and then you read, I should compute the correlation. So we are doing this. We compute the correlation coefficient, and then if you do this with R, you get already confidence interval, and you see it's a very strong correlation. And then, since I wrote my bachelor thesis in Poland about the spatial sign correlation, I computed this too. And it gives you even stronger correlation and confidence intervals which don't overlap, which means that they seem to measure something different. So it shouldn't be the case that the confidence intervals don't overlap if they measure the same. So these confidence intervals, they both require an elliptic distribution. It's not important now what this means, but an elliptic distribution, they measure the same, and probably it's not elliptically distributed. But we will now try to understand why they measure different things. So the reasons probably are these extreme points here. So robust, one is not interested in robust statistics, so we go to something robust. And probably the correlation is a bit more influenced by outliers. So we check this. This is the definition of the correlation coefficient you all know. And then we have here 20 data points or 25 data points, which aren't correlated from a multivariate normal distribution, so correlation should be 0. And indeed, correlation is nearly 0. Of course, it's not exactly 0 because it's just a sample. And now we manipulate the right point, and then we see that we can very much inflate this correlation coefficient and make it arbitrarily large or arbitrarily small by just moving this data point around. So we see that the correlation coefficient is highly influenced by outliers. And let's see what the spatial sign correlation is doing. This is this nice concept here. So instead of computing the correlation of our original data points, what we are doing is we project the data points onto the unit sphere. In this case, we are in 2 dimensions, so on the unit circle. And then we basically compute the correlation of these points. It's not exactly computing the correlation of these points. There are a little bit more twists into this, like we will see later. But it's the basic idea. So you compute the covariance of these points, then you get a covariance matrix, and then you don't compute the correlation like you know it from a normal covariance matrix, but you do this transformation, which is a little bit different. But you have to do it to get consistency under a normal distribution. but it's not so important to know this formula. All we want to see is that this thing is robust because we project all these points in the unit circle. So the same example again. This is the red point we have moved in the past, and now we move this red point, but effectively the red point is projected on the unit circle and then it's green. And of course, the screen point doesn't change much. It changed a little. So in the beginning, our covariant correlation was still the same, exactly the same. But then, yeah, of course, it changes a little bit, should be. This estimator should not be insensitive to observations, would be bad, but it's not influenced so much. So what we have learned now is that the difference of the estimations come probably from the fact that the empirical correlation mainly measures correlation from these extreme points, and the spatial sign correlation mainly measures the dependence of the central points. And now there is no wrong or right. I mean, you cannot ignore these extreme points, and you cannot ignore the center points. So probably what's interesting here is not to have one value which measures dependence, but a lot of measures, a lot of values which measure dependence. You want to measure the dependence of the central points and of the middle points, and probably also at the extreme points. And that's the idea of the talk. And to do this, we first have to define what means extreme or what means central. And we didn't need to start to do this because there are already tools to do this. You've probably, or some of you already know. So this is the concept of data depth. So the data depth measures centrality. So it's a map. Yeah, in this case in R2 to R with some properties. It should have the maximum value in the center, whatever maximum means. It should be affine invariant. So affine invariant means that if you stretch the data, then your measure should be the same. So it doesn't, it's not important how you measure your observations. So if you take a linear transformation, it stays the same, and also the depth. And the same is if you rotate the data, then the depth also should change. This is a property, then it should be maximum in the center. If you go from the center outwards, it should be, monotonically decreasing. That's important. And it should be zero at infinity. And one, data depth you more measure for centrality you already know. Or the easiest one is the Mahalanobis distance. You know the Mahalanobis distance. So just to use the chalk of Roland, the Mahalanobis distance squared usually of a point depends on the location vector and the covariance matrix. It's just the quadratic form. Of course, this is not going to zero if you go to infinity. So you have, if you want to transform it to a depth, you have to manipulate this a little bit. For example, this way. Then you have the data depth. But this is a parametric data depth. That's not what non-parametric statisticians like. So non-parametric statisticians like to have something non-parametric. So the most easy example is the Dürre depth. So the Dürre depth parts your observation space in two halves. So you want to know the depth of this data point. So you split your observation space in two halves. It's on here the left side and the right side. And then you count the data points which are on the left, on the right, and take the minimum of it. So the minimum would be here 2, and here a lot more. So this is the minimal half space. And the data depth is 2 over 11 also. I'm not sure how many data points I've sampled. And this, of course, works also in a higher dimensional space. But then we have a lot of half spaces. So it could be here, if you want to calculate the half space that was this point. You could look at the left, you could look at the right, but you could look at also at this space and rotate this a little bit around. And the best we can do is we can separate it into many points into only 3. So what we do is we rotate the space and look for the direction, which is just a minimal amount of points. And that's what we call the Touquet depth. And then you can calculate depth contours, or you can map the whole empirical Touquet depth about your space. So here is the depth contour where the Touquet depth is 0, and here it's 1 over 10, 2 and 3 over n. So then you get a whole map and contour lines. And of course, there's always a theoretical version of it. Then instead of counting points, you integrate over probability mass. So this is the same. So here the minimum half space in this point is this, and it has some probability mass. And these are the contours of the Touquet depth. So these 2 points have the same Touquet depth. And since it's a normal distribution, the contours of the Touquet depth, they are elliptical. Yeah, so it's the concept of the data depth. And now with the concept of the data depth, we can construct a correlation dependent on how far we are away from the center. That's what we are doing here. So we want to have something which measures dependence dependent on the data depth. So here we compute the conditional covariance. This is how you write a covariance. Conditioned on that the data depth is up. And you divide, like for a correlation, by division by conditional variances. And this gives you a measure of dependence. So we do this. No, not yet. This is a special case of a more general concept. And this concept we call, conditioned functional curves. So you can do it in a more general context where you just don't look alone at correlation, but where you look at the more general concepts and dependence of correlation by looking at more general functionals. So you have seen the functional for the correlation, but you can here insert any function you want and look at conditional expectations, conditional variances, conditional skewness, or whatever function you like, which depends on your data. And this we call T, and the alpha is for the conditional depth. So for very small alpha, it's are the extreme points. For large alpha, it's central points. And that's all we have to know about this. So then the question is, how do you estimate these conditional expectations? And this you probably know. You can, for example, do with another Ryer-Watson estimator. So if you want to estimate conditional expectations, what you do is basically visualized here. You use the weighted average instead of the conditional expectation. So if you want to compute the conditional expectation of y given x, for example, in this thread point, it would be logical to take into account the points which are close to the thread point. And that's what this estimator is doing. We can, for example, average about all points which are closer to the red point than the n. And then you get a value here, which is probably this. And if you're interested here, you average about this values. And that's what this estimator is doing. And now what we do is we use this, this rectangular kernel in this case, which means this point gets full weight, and this point gets 0 weight. And sometimes it's not nice, so often you use kernels which have continuous weights, and then you get a continuous estimation. So this we will use for our data depth slice. So our estimator is just the Dürre-Ryer-Watson estimator, but of course we don't know. Here we know the x value. Just take x here. But in our case, we don't know the data depth. So we take the empirical data depth. And the idea of this kernel is just that, yeah, if you just look at all points on the contour, the probability is large that there are no points on the contour, so you embed it into. So you use this bandwidth that you look at all points which are roughly not too far away from this contour, and you give them weights which are 1 if they are close to this contour and low weights if they are far away. But then, if you get more and more data points, you make this band here smaller, because now you have enough data points to ignore this point here, which probably has a different expectation. So your bandwidth gets smaller and smaller. Only that's the only way how you get consistency. Your bandwidth has to go to 0, otherwise you get a biased estimator. But if the bandwidth is too large, you have too much variance because you have no observations. So you need a bandwidth which goes to 0, but not too fast. Yeah, now we can compute our estimator for our dependence between light intensity and the population density. And we use a triangular kernel to get something which is continuous in estimation. We use the spectral, and then we see that the dependence is very large for the central points and smaller for the extreme points. And that's exactly what we expected when we looked at these two different correlation estimators in the beginning, where we had this spatial sign correlation, which was measuring this, and the usual correlation, which was measuring this. And we argue that this gives us more information than just one dependence measure. And this is nice, but you can say maybe this is just randomness or measuring something which is not interesting. So we need some theoretical guarantees. And the first is consistency. So we want to have that if we have arbitrarily much observations that you converge against the right value. And luckily, there are already consistency results for the Naira-Watson estimator. But the proof is also not extremely difficult. You mainly compute the mean squared error of your estimator and hope that your conditional expectation is somehow continuous or even differentiable. So showing this is not extremely difficult. Our main problem is that we don't observe the right depth, but we only observe the estimated depth. And then we don't know if we have only the estimated depth, our estimator still converges. So we have to control the difference of the estimators. If you know the depth, then you can estimate the depth. That's our main problem here. And yeah, just to visualize our situation again, that was, we are looking at the minimal half space. And this is a normal distribution. We want to compute the depth at this point. So the minimal half space is here. And it has some probability, which we can see here. So we are now, what we will do is we will rotate this half space through this blue line, and then look for the minimal half space. So now we are at this point and have this probability. But we also have an empirical depth, and this is just counting points. And I visualize it green. And what you do is you rotate the half space, and then you are now at this point, and you see the theoretical half space is larger, and the empirical half space is also larger. And this is what you do, you rotate around and look for the minimal value. And then the difference between these minimal values, that's our problem. Because this is, yeah, we replace this value by this value. And then the question is, does it still work? And I mean, the easiest situation would be if this green curve here would uniformly converge against this black curve. If it converges in all of these points, then also the minimal values would converge. So this is mainly the strategy which you apply here. And to do this, you apply empirical process theory. So empirical process theory, I'm not completely sure how much you know about this. Yeah, looks exactly at somehow uniform convergence of the transformations of the original random variables. So what we want to show in our proof is that uniformly the difference between the estimated and the real data depth is of order, yeah, it goes to 0 like square root of n. That's what you want to show. And if you know what this empirical data depth is, it's just an estimated probability. You know that it goes pointwise to 0 like square root of n. That's a central limit theorem, basically. But we want to have this uniformly about all these half spaces, about all these x's. This is a challenge. And I mean, we are not the first one doing this, but I will explain how you do it in general. And we use this framework later in a more involved proof. I will really show in a new result, but this is an old result. So we want to show that it uniformly converges in light speed. And we go to something which we all know. So just to make the situation a little bit easier. And we all know the empirical distribution function. And this is somehow a similar problem. So you know that the empirical distribution function converges against the theoretical distribution function, and it converges uniformly. So if our sample size increases, we converge uniformly against the true function. And then the next question is with what speed? And yeah, in every point, we converge the speed square root of n. And we also converge uniformly with speed square root of n. And this should be very familiar to you, the line at the top. That's exactly the test statistic of the Kolmogorov-Smirnov statistic. So you can test with the test statistic if the distribution is the distribution we assume. And yeah, Kolmogorov could show in the 30s that this converges uniformly with speed square of n. And as you see this, now I plot the difference between the empirical distribution function and theoretical values. You see this? Then this converges against some kind of process. And this process is not sure how much you know about processes. It looks like a Gaussian process, like a Brownian motion. But it's a special Brownian motion because in the last point, in point 1, it's 0. So it converges against a Brownian bridge. That's a Brownian motion conditioned on the last value is 0. So this is a fascinating result. But then people said, does it only work with these indicator functions? Or could I look at more general cases? I mean, we are interested in half spaces. Half spaces are also indicator functions, but a little bit more complicated. So the question that people were asking in the 60s and 80s, can we substitute these indicator functions by general functions? As we already discussed, by general functions f. So now this here is a function of this xi, and this function class is defined by this end of the interval, by the small x. So we look at all these indicator functions by all these half spaces. Yeah, and this gives us a function class. And now the question is, can we put here arbitrary functions depending on xi? Just arbitrary f's. And then we look at all f's jointly together. In the past, we identified this axis here as the endpoints of the intervals, but now we are just random, not random functions, but a more general function class. And the fascinating result people derived in the 80s, like Dudley, is that it works indeed. So you can look somehow at arbitrary functions, and it converges against some general Brownian bridge. So a Gaussian process whose covariance structure is defined by the covariance of these f's. And this is what we understand as the Donsker theorem. And there's two restrictions. The first restriction is, of course, pointwise. This is here the central limit theorem which we use. So this means that your functions have to have a variance. If you don't have a variance, there's no central limit theory, so there's no chance for a Donsker theorem. So you need that your variance is finite, and you define not the variance pointwise for every f, but you define an envelope function. It's a function which is larger than all the functions you can look at. So in our case, we are looking at these indicator functions for function f and x. That's I, where just indicator functions x smaller than I. These are our indicator functions. And now we need a function which is larger than this function for any I. So we have to bound it above. And it's easy to find a function which is always larger than the indicator function restricted to I. It's just a function which is constantly 1. This is obviously always larger than this. So we can use here as the upper bound function, as angular function, the identity, and this is finite. So this is fine. And then we have to make sure that the complexity is not too large. And then there's different ways to measure complexity. So the easy way is to use the Wagner-Chenoweth dimension, which people from computer science sometimes know very well about. So it's a little bit difficult to explain. But it somehow measures how many points you can split, you can scatter. And the funny thing is, if you look at these intervals from the empirical distribution function, you can only scatter 1 point. So the Wagner-Chenoweth dimension is 1. And for our half spaces, we can scatter d plus 1 point. So the Wagner-Chenoweth dimension is d plus 2, which is in particular finite, which means that we can apply the theorem. So we apply the theorem for our half spaces, and this gives us our convergence speed of square root of n, which gives us our consistency. What is this result here? You need some assumptions like Lipschitz continuity of the kernel, but that's not a problem. You can choose the kernel yourself. And then you need this rate here, which is a little bit more restricted than the rate of the original Nadal-Heyerholz estimate. Yeah, but this is not sufficient. You also want to have asymptotic normality. If you have asymptotic normality, you can express the variability of your estimation, your uncertainty of your estimation. And there we have also a nice result that pointwise, for every fixed alpha, we converge against the normal distribution. And the limiting variance in the normal distribution is extremely easy. It is some integral about the kernel. I mean, you choose the kernel, so you know the integral, and some conditional variance. But the conditional variance is not so much a problem, because this is just a conditional expectation. It's a conditional expectation of the kind we have treated here. So here we have exactly shown that we have consistent estimator for such things, so we can estimate it without problem. And yeah, the proof gets more spectacular. So it's not enough to know that this goes to 0 with square root of n, right? Square root of n. That's not sufficient. You need more speed, more knowledge. But I mean, you don't have more speed. But what you do is, we rotate the data again. We make 2 errors here. One error is that we look at the minimal half space and compare the theoretical probability with the empirical probability. This is a manually random variable, or binomial distributed random variable. And we have central limit theory. And this says variance n, or speed square root of n. So we can never be better than this speed. But if we know that this is manually distributed, we can use this in the proof. And this term will somehow disappear because it's just an unbiased thing, so that's expectation 0. You know the variance, so it's very easy to control. But you have a second error, and that's that the empirical minimum is not at the same point than the theoretical minimum. That's the xi. And for the xi(n), we developed a bound, also based on empirical process theory, which says that this is order n to the power of -2/3. And this is what we need. We need something which goes faster to 0 than square root n. And this here you can somehow see as a bias term, because this will always be negative. And this here you can see as a variance term. So this dominates the variance, this dominates the bias. And if you use this nice result, then yeah, you can show what we had wanted to show. Yeah, here's what I said. It goes to 0, like 1 to minus 2 over 3. Then there are some regularity assumptions. One regularity assumption is that the quantity of the data depth is not too exceptional. So you want to have it relatively smooth. If you have a smooth depth quantity, then you have a uniquely identifiable minimal half space. If you have these points where you're not differentiable, is not differentiable, then you don't have a unique half space. And then the proof somehow fails. In these points, I cannot bound the error like I've shown before because there's no minimal half space. And this creates problems, but as long as you have finitely many, this is the proof, you can ignore it somehow. So even such a somehow special depth point, you still find for. So now we go back to the more applied part, stop with these theoretical things and look more at pictures. So now this is the confidence interval for our correlation. And now we see that there indeed is a difference in the data points and the more extreme points, and the dependence of the more extreme points compared to the dependence of the normal points. And here, with these dots, you see the usual correlation estimation. You see that the normal correlation does not represent the data very well. Only in this small part of the solution. Then we can see in simulations if this works indeed. So we take a very easy setting, IID random variance from a multivariate normal distribution in 2 dimensions. And then we look at the conditional variance. So we say that we set the expectation to 0, so this is a conditional variance. And we look at the depth of 0.1, so extreme variance, normal variance, variance of the inner points. And this is a conditional function curve. Yeah, you can imagine that if you're at the center of the distribution, there's no variance. And if you go to the borders of the distribution, then there's a lot of variance. This is the asymptotic variance. And this is the density of the depth, which is not so important. And now we simulate and we estimate our conditional correlation. We do this 10,000 times, and then we compare the empirical distribution function to the true distribution function of the limiting normal distribution. The limiting normal distribution is in black, and yeah, the empirical distribution function for 1,000 data points is here, for 2,000 the yellow is here, 4,000 green here, and for the blue 8,000 we are basically perfect. But this only works for the extreme points. If we go more to the center, then we see that we have a large bias here. Even if we have 60,000 data points, we still have a large bias. And this comes from our bandwidth, which goes too slowly to 0. Here it's just 10 to the power minus 0.2. This goes too slowly to 0 to remove the bias. But our theorem says we cannot do it larger than 1/3, so there's not a lot of space to improve this. So we don't really trust the estimation of the confidence intervals for the very small data depth. That's what we learned here. Then we look at our example again. So we look at the dependence between light pollution population, and now I add a third variable. And this is the number of companies in this data district. And now we have 3 variables. Now we can do a principal component analysis. I mean, we can also do with 2, but then it's not really interesting. So principal component analysis projects the data onto the directions with the most variance. So this is the direction of the largest variance. This is the first eigenvector, it's the eigenvector to the largest eigenvalue of the covariance matrix. And it says where's the most variance. And this is the direction of the second most variance. And here we plot the eigenvalues or eigenvalue decomposition. And you know, the larger the eigenvalues, the more variability you can explain of your data. Now we condition on small data depth, and then we see that we can yeah, we need basically two principal components to explain all the variability. We see that the second principal component explains a lot of variability. But if we then go more to the extremes, we really need all the three principal components. So now the third principal component explains variability. That's what we are seeing here. And now we can look at the directions, which are even more interesting. Now, in the first plot, we see the first eigenvector. And the first eigenvector has three components. And these three components, yeah, they define the direction of this eigenvector. And we see that all these three components are positive and into the same direction. So the most variability we explain by going into, yeah, all the, by, yeah, distributing, now should I explain it by basically by this eigenvector, which means it's a linear combination or even the average of all the three components. That's maybe the best explanation. So the first is just the average of population, companies, and light pollution. The second one is more interesting. So for the small values, you see that this is basically measuring only the blue line, the number of companies. So they are relatively close to zero, or even contrast between companies and light and population. But if you go to the extreme, then it's a contrast between population and light. So the second principal component distinguishes between light and population. And the third principal component is for the central points contrast between population and light. But for the extreme points, it's a contrast between companies and light. So the directions they change, we go from the center to the extremes. If you go to the extremes, then it seems to matter more what the population is if you want to predict the light. Yeah, and I think that's it. I don't think I think we want to finish or do you want to see this? I don't. Me too. You want to see? Like to see. Okay. Now we see how much is our depth condition correlation curve influenced by outliers. So we go back to the correlation estimation. Bivariate normal distribution, no correlation. This is a red curve, and it's flat, like it should be. If you go with normal distribution to the borders, there's still no dependence. But now we add an outlier with the coordinates delta, delta. And delta, delta is visualized with this color scheme. So delta, delta here is black. It's the dot groups. If it's 10, it's the green one. And if it's violet, it's here at the top. So you see that the depth conditional function curves influence, but only if you go to the extremes. That's what you expect. And it's more influenced if your outlier is larger. It's also what you expect. But the inner points, they don't change. So the correlation of the inner points not change because it's just one outlier. And then you can also look at more outliers. So now basically the same setting. We start the bivariate normal distribution. But now we don't add one outlier, but m outliers. And m is coded here. So black means no outlier. You already know this roughly flat. And violet means 200 outliers. And yeah, you see the more outliers, the more we manipulate this depth conditional correlation curve. But still, the inner points are not much influenced. But you see that the influence begins very little. That's also what you expect. If you have more outliers, and then already the inner part distribution gets a little bit manipulated. Yeah, that's what I wanted to propose to you, that where the depth conditional correlation curves or functional curves. And the idea is really sometimes you cannot describe the location or variance of a distribution with just one variable, especially if the distribution is somehow skewed. But then you can apply this depth conditional functional curves, then you get the whole complete curve describing the dependence. So this gives you additional information about the distribution. And we have also some, we're working on some improvements for this. For example, having used statistic techniques there so that you can construct even more general depth conditional functional curves.